All right, Trinity's here. Admit. Okay, cool.
How you turn off the camera?
How do you turn off the what?
The camera.
I think, okay, at the bottom of your screen, I don't know if you see the bottom of my screen, but at the bottom of your screen, there will be 3 buttons. The one on the left is your microphone. The one in the middle is hang up and go away. And the one on the right is your camera. And if you have a slash through it and it's red, that means you've turned off your camera. So right now, I don't have a camera, so mine's already red, blacked out. All right. Let's see. It says I'm recording. Okay, so let's give it a try here. Okay. Let's see. I'm gonna try my new stylus today. Anybody got any questions? I was quizzing Leela about the rest of her classes, and she said it's going fine. Anybody got any questions about registration that's about to start happening, or about things on campus?
No, sir.
Okay, I mean, if you do, you know, I'm somebody that you can shoot an email to, and if I don't have the answer, we'll find somebody who has it. Okay. All right, I'm going to end with that. Done with that? Cool. All right, let me go back here. All right, here's where we were before. Redox. And we had some big take-home messages last time that you can't have one without the other. I know y'all recognize the yin-yang symbol. And so if electrons are lost, they must also be gained. You can't have reduction without oxidation. You can't have oxidation without reduction. Okay. Hey, Maddie. All right. So talked about that. Let me go to the wrong side. All right, come back over here. All right. So let's take that idea and see if we can't figure out what the heck's going on here. So have y'all ever seen this before? If you haven't, you can take a second to read the advertisement. And so I don't see Miriam there. I'm going to miss. And Miriam's our marketer, so I don't see that one. All right. I know you probably know that really nice silver jewelry or silver teapots or whatever will get tarnished. And tarnishing is going to be a silver compound. So in other words, silver metal is what you want. What you'd like is that nice shiny silver. But unfortunately, if you leave it sit open in the air, it will get oxidized and it forms silver 1 ions on there. So my first question is, how do you know that the silver is oxidized in this process?
Isn't the tarnished rust a version of rust?
Yeah, but rust is a word we reserve for iron, right? But yeah, you're exactly right. It's the silver version of rust, if you will. Okay, so how do you know? If I gave this to you on a test or a quiz, and the next quiz, I don't know if I mentioned to you. Let me show you real fast. It says on the outline, the next quiz is going to be March 31st, if you check. I think I put it for the Thursday after spring break. So I want everybody in the room, I want everybody here to be convinced that this is oxidation of silver. When this right here becomes this, you got to be convinced of that. How do you know it's oxidation?
It lost an electron.
Perfect. That's the point. If something loses an electron, and that's the way you become more positive, you become more positive by losing an electron, that's oxidation. And so this is a good example of natural oxidation. So take a second and read this for a second then. All right, this is a product they're going to sell you, which is supposedly going to prevent that. An anti-tarnish plate without harsh chemicals. That's kind of interesting. Endless scrubbing, noxious odors, of dirty hands. Environmentally friendly, and this is obviously my favorite comment, chemical free, because apparently there are no chemicals in this picture. A chemist would take exception because everything in the picture is a chemical, but that's okay. We won't go there. All right. So let me ask you. Let's say you don't want your silver to look like that, you know? So you could be in a museum, you could have jewelry. I just don't want my silver to tarnish. How do you stop that? how do you prevent that?
Doesn't the plate act as a reductant?
It will have to. It will have to. That's exactly right. But without the plate, if I put my silver teacup on the shelf and I want to prevent oxidation, what would I do? What do most people do if they want to keep things from old things from oxidizing? Do you store it out in the direct sunlight in the backyard? No, you wouldn't do that. So you would try to store it in an isolated place, usually a dark place, because the light energy can help oxidation. When you want to prevent that. And then some of the things they'll do is, as we mentioned, like with old manuscripts, is they'll actually use gases like argon. If its stuff is really valuable, they'll put it under an inert atmosphere, and that will prevent air, which is the oxidizing agent, from getting to the silver. Okay, so we're going to leave this slide for a second. I heard somebody say, they said, this plate down here has got to be the reducing agent. I mean, it has to be. The only way to counteract oxidation is to be the reducing agent. So we'll talk about what that plate is made out of before we're done. All right, any questions on this before we go? Everybody leaving this slide should leave convinced that if the roaster gave me that picture on a quiz, then I could tell them that the silver metal was being oxidized because it lost electrons. I think that was Dylan or somebody that chimed in. All right, we okay?
Mm-hmm.
All right. Okay. Surely you've heard of lithium batteries, right?
Mm-hmm.
So why in the world would they say that? This is a package, I don't know, I got from Amazon or UPS or something, came to my house. Why in the world would they say that? Who cares if it contains lithium metal? Who cares? Is there danger? What do y'all know about laptop computers, especially laptop computers, or even electric cars like Teslas that have big banks of lithium batteries? Is there any danger with those?
They're highly reactive.
Yeah, what is highly reactive?
Lithium.
Yeah, so I got to ask you a question. I'm going to write down two. Is this the guy that's dangerous? Or is this the guy that's dangerous? And does it make a difference? Are they different? Maybe you may remember from lecture that I took this metal, remember that? Piece of sodium, and I put it in a beaker, remember, right? And I had a little piece of sodium sitting on top. Remember what was happening? Because lithium's in the same family as sodium, so you're figuring it might do the same thing. Do you remember what happened with that piece of sodium that I put on top of the beaker?
It dissolved and bubbled up.
Yeah, hissed like crazy. I don't know if you remember, but I was holding it as far away from my face as I could so that you all could see it. I even put like a mesh on top that if any reaction took place, it wouldn't explode and throw chunks all over the people that are sitting in the front row. See, Alexa? See, so you're sitting like in the front row, or in Eli, that could have been bad, right? Mm-hmm. So the idea is that this guy right here, I'm putting an exclamation point, is some pretty nasty stuff. Sodium metal is dangerous. And what's happening right here, what makes it so dangerous, is the sodium metal, which has no charge, is becoming sodium ions and releasing electrons to somebody. That's happening right there. So which of these two, lithium ions or lithium metal, do you figure then is more dangerous? And which is more dangerous, sodium metal or sodium ions?
Metal.
Ions.
Is sodium dangerous when it has the electron, or is sodium dangerous after it's lost the electron?
When it has the electron.
When it has the electron. And if you hopefully y'all have a periodic table. That's one thing I forgot, but hopefully you got a periodic table around. We all talked about the fact that sodium is one electron away from neon, right? Neon is like nirvana, super stable. And sodium, if it loses one electron, could become like neon. And sodium has one goal in life when it's the atom, and that's to become like neon, lose that one electron. Lithium, if you look, he wants to be like helium. Helium's only got 2 electrons, and he's so stable that you can give it to children in balloons. This guy is 1 electron more than this guy. If this guy loses that electron, he'll become like helium. And so let me ask you then, which of these 2 things, lithium ions or lithium atoms, are the dangerous side of lithium?
Atoms.
I heard Mike. What did you say, Mike? Somebody?
Atoms.
The atoms. And why are the atoms the dangerous side?
Because they want to lose an electron.
Mm-hmm. This guy wants to lose because he wants to become like helium. And so if this guy wants to lose, does this guy want to be oxidized or want to be reduced? Wants to be oxidized. So take a second then, and let's say that you're a lawyer and you work for UPS. Why would your lawyer be happy that you put a sticker like that on the package? What's comforting from the legal sense about a sticker like that on the package?
It's not dangerous. It's
What's
not
that?
dangerous.
Does it contain the dangerous kind of lithium or the less dangerous kind of lithium?
The less.
And so you're figuring that you know there's some lawyer at UPS, there is, right, or FedEx. There's some lawyer that says, sure, if you're selling a package that has lithium in it, you better put that sticker on there so that people can't sue us. I mean, that's true, right? And so this idea of some metals being easy to oxidize, and we're going to see some metals are hard to oxidize, is a big deal. So any questions on this page before we leave it? I'm just using this as an example to show you that redox is everywhere. Okay, go to the next page. All right. Now this is my analogy. Okay, I'm going to use an analogy. What I'm going to do is I'm going to contrast these guys up here with these guys down here. And I want you to stop and think. You may not know what these are. This is platinum, that's silver, and that's gold. Think about what you know about platinum, silver, and gold. Where does the average person encounter platinum, silver, or gold? Devin, could I buy platinum, silver, or gold at Kohl's?
Yes, the jewelry.
You mean there's platinum jewelry at Kohl's? And there's silver jewelry at Kohl's and gold jewelry at Kohl's?
Yeah.
So let me ask everybody, why in the world do you make jewelry out of platinum, silver, and gold? Because they're so darn expensive.
They won't tarnish as easily.
Okay, let me write that down. Okay, so let me write that down. They don't tarnish. No tarnish, which is a good thing, right? So then it won't look all awful. I mean, if I'm paying that kind of money for that ring or that earring or that necklace, I don't want it to turn black. I want it to be nice and shiny. Devin, I'm sorry I keep picking on you, but you've got the jewelry experience that none of the rest of us have. Devin, did any people have any trouble with this guy? Nickel? Are there some people that come in and they say, I don't know about those earrings. Those earrings.
Oh, yeah. They're like, I need nickel for earrings because it irritates their ears.
Wait a minute now. So this guy is an irritant. You guys probably know that if I leave some metals, nickel is a good example. If I leave some metals in contact with my skin, I'm not one of these, but some people are. Some people are really sensitive to nickel. And let me tell you a little bit about nickel. You don't have to know this. Nickel is a metal that oxidizes easily, kind of like lithium, sodium, and zinc. Okay? And so think about it. If I put that nickel jewelry in contact with my skin, the nickel jewelry in contact with my skin will undergo oxidation, which means a chemical reaction will happen in contact with my skin, and that might give me a rash. So let me go back. So these don't tarnish, but then they also are not very reactive, and because they're not very reactive, if I keep them in contact with my skin, they're likely not to do what nickel does. So my point in bringing these up to begin with is that metals fall in categories. Some metals are easy to oxidize. They lose electrons no problem at all. Other metals, which is why they're so valuable, are really hard to oxidize. And that means they don't lose their electrons very easily. So what I want you to do, we'll pause for a minute. Let's take this one example right here, okay? And let's go back and let's do a review. We're going to do the lake and dam analogy here in a minute. But I'm going to take this silver and lithium example, and I want to go back over here, and I want to work this out. All right, let me write down what we just had on the last slide, okay? All right, I had lithium plus silver ions, and these guys are going to become lithium ions and silver metal. So oops, sorry. Okay, silver metal. Okay, got it. All right, what I want you to do is I want you to write down the two half reactions like we did last time. You may remember that whenever you have redox, if you have the yin and yang, any redox reaction can be broken down into two half reactions. One of the half reactions is oxidation. One of the half reactions is reduction. And so I'm going to give you a few minutes to do that while I go get a drink of coffee over at my coffee pot. I'll be right back. So what we're looking for is I'm looking for the oxidation half reaction, and I'm looking for the reduction half reaction. And oxidation is going to involve either this guy or this guy, and reduction is going to involve either this guy or this guy. So who's got an idea of which of the two things is being oxidized in this reaction?
Wouldn't it be lithium?
Who's being oxidized?
Lithium?
Okay, so oxidation, help me remember, what is oxidation? It's electron
Losing an electron.
electron loss. So the guy that's losing the electron, this guy has no charge, right? And now he's got a charge. And the way you get there is by electron loss. So it stands to reason that reduction has got to be the other guy. It's going to be electron gain. This is going to have to involve the silver ions. And this is going to have to involve the lithium metal. And so if I was to write those, what happens to lithium? What's he turn into on the product side?
A lithium ion
Mm-hmm.
and an electron.
And which side did the electron go on?
The product.
Product side. Because look, only if I put a negative and a positive together do I get equal to the no charge on the reactant side. What about over here? Comes silver. And which side do I put the electrons here?
Reaction.
Yeah.
All right, let me stop for a minute. Everybody in the room has got to be convinced that these are balanced. And notice that this is electron gain because electrons are being gained. And notice this is electron loss because electrons are being lost by the lithium. And if I was to go up there and I was to add these together, then, because you can add them together, what's the idea when you add two half reactions? Remember what we did last time? Well, what do you have to worry about when you add two half reactions?
Common multiple or something like that.
Yeah, and so what's the common multiple here? Will these electrons cancel? Do I have to multiply by anything?
No, I don't think so.
It looks like we're all set, right? It looks like this one electron will cancel that one electron. And I can bring all this stuff down. That's this guy. That's him. This guy is this guy. And this is the other product. And my other product is this guy. So it turned out it was balanced. It was balanced already right from the start. But at least we broke it down into the two half reactions. All right, so let me stop and answer questions because what we're doing now, breaking reactions down into half reactions, is a skill you have to have. You got to be able to do what we just did. You've got to be able to identify who is oxidation and who is reduction. Anybody have any questions you want to ask me? Okay. Let me go back then. Let's go back here. All right. So why is water behind a dam valuable? Why do we make dams? Because they're all over the place. Why do we make dams?
For energy. Okay,
energy is one thing, right? Because you can use the falling water. This is supposed to represent my turbines. You can have the falling water, we generate electricity, right? You could also use water for recreation, but I'm talking about the energy thing. So the idea behind here is the lake behind here is stored energy, don't you think? And so I should ask you the question, how did the water end up behind the dam in the first place? What brings the water to behind the dam? It's kind of relating to something we talked about back in chapter 5. Or rather, chapter 5. So how does the water get from the Pacific Ocean to Greers Ferry Lake?
Rivers.
Rivers is one way, but how does the water get in the river? How do you get from the Pacific Ocean to the White River? It's going on right now. If I put on the Weather Channel, we would see it going on right now.
Rain.
Rain and snow, right? And so something to think about is another thing about is that lake and stored energy. This is really another form of stored solar energy. The sun makes water evaporate from the Pacific Ocean. Wind blows it over the United States and it falls as rain and then ends up behind the lake. That's stored energy. Okay. All right. So now here comes my analogy. How is this lithium atoms and silver ions? And I'm going to encourage you to pay close attention. You cannot be careless with those charges. You need to pay attention when the charges are there. How is lithium metal and silver ions like water behind the dam, like stored energy? That implies that something wants to happen, right? We all know that if the dam bursts, I've seen enough in the movies, we all know that if the dam bursts, the water will come pouring out. So the water wants to flow. I got to ask you, does lithium want to be oxidized?
Yeah.
Yes.
Because it's easy to be oxidized, right? And think about this. If silver metal is difficult to oxidize, what does that say about silver ions going the opposite direction? Which is the opposite of oxidation.
They gain.
Yeah, it says that if this guy doesn't want to go that way, then what wants to happen is this wants to happen. Okay? So you can think about metals that are difficult to oxidize. The counter argument there is that means their ions very, very readily like to gain electrons. They want to turn back into the metal. These metals are happy as metals, okay? And so the reason why this works in batteries in your cell phone is if I pair a metal that wants to be oxidized with an ion of a metal that's difficult to oxidize. So this guy wants to become this, and this guy wants to turn into this. That's a source of energy, like water flowing out of a dam. This wants to happen the same way that water through a dam wants to flow, except it's electrical energy and you design it in the battery. What I'm trying to get across here on this point is where the energy comes from in a battery. In a battery, you put on one side of the battery one thing that wants to be oxidized. You put on the other side of the battery somebody who wants to be reduced. And when you pair them together in a battery, you can use that desire for electrons to flow to generate electrical energy to run my phone and my laptop. How are we doing? Questions? I'm gonna take a drink of coffee. Can you all see my full screen? Okay.
Yeah.
Okay. Because if you can't, I'll move it over. Okay. All right. Let's try the next one then. All right. Take a second now and read these two phrases, both of which are true. This sounds like a good quiz question. What am I talking about?
So sodium metals are the dangerous ones, and sodium ions are the nutrient.
Okay, we got to vote for the metal is dangerous and the ions are safe. Anybody have an alternative explanation? You and I have to have sodium to live. If we don't have sodium, we die. And I mean, we need about 2 grams a day. So we pee out and we excrete out about 2 grams. So we got to keep eating about 2 grams of sodium. But the question is, what form of sodium nutritionally do we have to have? The metal or the ion? Which form? Which one's the safe form to be in our body?
Ion.
Yeah, ion, this one's safe. And I've showed you a couple of times, at least once, right? Just how dangerous is sodium metal. And why is this guy so dangerous?
He wants to be like neon.
It wants to be like neon. So it wants to lose an electron or gain an electron.
Lose.
And so that's oxidation or reduction.
Oxidation.
Sodium metal is a dangerous metal because it's easily oxidized. You think iron rusts easily. Sodium rusts very, very quickly. Okay. All right, so now I got a question. We're going to start talking about battery parts, all right? And batteries, as we'll talk about later, all have a positive end and a negative end, okay? Here's my question. You probably know that that one's 1.5 volts, and you probably know all of these are 1.5 volts. How can they all be 1.5 volts? Different sizes? That wasn't my dog. And I silenced my phone today. How can these all be 1.5 volts if they're different sizes? That doesn't seem to make sense to me. And
Do they have different metals?
To be honest, that's actually a good question. I heard somebody say, is it different metals? In other words, different ingredients. And to be perfectly honest, all of these batteries, these are different products, so they might have slightly different metals. But for the most part, like if I bought AA Duracell and C Duracell and D Duracell, Duracell's putting the same ingredients in all of the batteries. So for the most part, the ingredients are absolutely identical. But before you answer that question, let me ask you a question. What do people use AAA batteries for, and they use D batteries for something else? What are the kinds of things that people use AAA batteries for?
Like TV remotes.
Okay, so like remotes. Is that Matt?
Yeah.
So Matt, is that a small object or a large object?
Small.
Okay, let me write that down. It's kind of a small object. Duh, because it fits inside a remote. What do people use D batteries for?
Like smoke alarms.
Okay, smoke alarms. One example. I think they use 9-volt batteries for smoke alarms. What about the people who are on spring break? Not you, because you guys are in class. What about people that are on spring break down in Miami? Where might they use a D-size battery?
Like some speaker, like some giant.
Yeah. What's the whole point of a speaker on the beach? What do you want a speaker to do on the beach?
Be very loud.
Loud. And to be honest with you, to move a speaker, to drive a speaker takes a lot of electricity because a speaker literally is like a diaphragm that has to move in and out. And so sometimes you need monster amounts of electricity, and other times you don't need so much electricity, and other times you need a little bit, and other times you need a little bit more. And so whoever designed these batteries said, hey, look, let's make them all 1.5 volts. But what we're doing is we're going to change one thing about them that allows how they deliver the electricity to happen. So I'm going to show you that in an analogy. What is the difference between a dam where I have a big gaping hole and a dam where I have a little tiny hole? Still got water behind the lake, and I still got water behind the lake. It's the same size dam. What would be the difference if I was standing right here? Would you notice the difference? Same lake on either side?
Wouldn't there be more water coming out of the right side?
Uh-huh. More water. I'm going to add an exclamation point, right? How does that relate to different size batteries? What flows? in a battery? What do you call that thing that floats? Electricity. I heard it. And then what else? It's another word they'll use. Have you heard this word? Right? The current. The current is literally the number of electrons that are flowing. And so which one of these monsters do you figure will cause more electrons to flow faster? The D or the AAA will cause more? The D. This is the reason why they make big fat batteries like this. It's like the same size lake on the same size dam, but the one difference in a D-size battery is everything's larger. And if it's larger, more electrons can flow, not necessarily faster and not with more energy, just more. And so if I want to drive that big speaker on the beach at spring break, I need massive amounts of electrons to flow real quickly. And that's what a D-size battery will supply. And so the idea to appreciate is that all of these have electrons, same ingredients, same energy, but one can deliver current, much faster current than the other. And so the unit for current is called an amp, if you want to know. So if I put my finger in a light socket, it's the amps that tends to kill you because your body is not designed to have current flow through it. So that's that. Any questions on this one? All right. Well, here we are. We're at the parts of any battery, okay? So before we do that, I want to go back to this, and let me clean this off. I'm going to draw. Let's say I'm you, and I'm alone on a test or a quiz. Because none of us are going to memorize battery reactions. I'm not going to memorize them, and you won't memorize them either. But I could give you pictures of a battery and ask you intelligent questions about it. So let me draw a battery. Battery's got a positive end and a negative end. And let's see, I could take the battery and hook a wire, couldn't I? Right? And the cell phone, if I had a cell phone, my cell phone would be right here, or my speaker's on the beach, right? And so now let me ask you some questions. Let's say you're an electron. And you're an electron in this wire. Which way will you flow? Are you going to flow? Think carefully. Will an electron in this wire flow clockwise or counterclockwise? This is how I keep it straight. I draw a picture and I keep it straight.
Clockwise.
Okay, so semi-clockwise. Let's see. Clockwise is this way, right? And counterclockwise is that way. Isn't that right?
Mhm.
Which one do you want? Clockwise or counterclockwise? Now these guys are negative, aren't they?
Mhm.
Which means they have a desire to go where? Do those negative guys want to go toward the negative or away from the negative toward the positive?
Toward the positive.
Yeah, I mean, you're an electron. You got one goal in life, and your goal is to go to the positive side, wouldn't you say? And if I was an electron over here, I would want to be leaving the negative side if I was an electron. Does that idea make sense?
Mhm.
And I don't ever memorize it. I draw the picture, and whatever makes sense to me in the picture is the way I know the electrons are flowing. So let me ask you a question then. Okay. This side over here of a battery, is that side of the battery consuming electrons or producing electrons?
Consuming.
All right. So overside on the battery, which one of our terms is electron consumption? Is that reduction or oxidation?
Reduction.
This has got to be electron gain. On the positive side of a battery is where electrons are being gained. If I was to go to the other side of the battery, let's see if this makes sense, then what has to be happening to electrons on the other side of the battery?
Oxidation.
Yeah, got to be, which is loss or gain. It's going to be electron loss. Okay, you got that idea in mind? And so the idea of a battery is on one side of the battery, I put somebody who wants to lose electrons. On the other side of the battery, I put somebody that wants to, and I put them inside a little thing and I sell it to people at Walmart. That's the whole idea. Let's come back then. Let's come back to my picture. All right, let's take a look at this picture just for a second. Electron, I'm going to draw electrons. Which way are electrons flowing through this wire? Clockwise or counterclockwise, according to my picture?
Clockwise.
So electrons are leaving the negative side or going to the negative side?
Leaving.
Leaving the side, right? And so they're going up this way, right? And they're coming down this way. That's electrons. So that would be a counterclockwise motion, right?
Yeah.
What happens over here? Reduction or oxidation? And how do you know it's reduction?
Reduction. Because
That's
it's
where electrons are going.
gaining electron.
Mm-hmm. And how do you know what's happening over here?
Oxidation because it's losing electron.
Leaving. Now, more jargon. I'm sorry, but we got to have more jargon because we didn't have enough. Surely you've heard these words, right? Cathode and anode. Have you heard those words? All right, well, we got to get used to the words, okay? So get ready. The word cathode, forever, and for the rest of your life, forever. The word cathode, forever. And let me say it one more time. The word cathode, forever. I mean always. You mean sometimes? No, I mean always, forever. And I'm saying that because it's always true. The word cathode means reduction. So for the rest of your life, if you ever see the word cathode, that's the $10 word that means reduction. And what does it stand to reason that anode means?
Oxidation.
Has to mean oxidation. If you ever hear anybody talking about anode, that means oxidation. So I'm going to do an example. Let me just clean this off. This is a true story. Y'all know Dillard's department store? So years ago, when my kids were young, we go to Dillard's with my wife, and we're walking in, and they had these pots, right? And at Dillard's, I was looking at these pans, like soup pans, right? And then they had the price tag on there, right? There was the price, and I took a look at that price tag, and I thought, "Are you kidding me? That's a pan. How did they get away with charging so much for a pan in Dillard's?" And I have to say that the salesperson was right on point. Okay, so they were properly trained. The salesperson says to me, this was their reason why the thing was so dang expensive. They said, "Yeah, but it's so expensive because here's the word, it's anodized aluminum." Oh, and then I was convinced right there. It said anodized aluminum. Now I can see why you get so much money for it. Okay, well, you all are an expert on these words. What the heck does that mean?
Oxidation.
Does that mean my aluminum in my pan is oxidized or reduced?
Oxidized.
Oxidized.
Y'all see them using the term? I mean, if you looked on the side of the box, that's why they charge so much, because it was anodized aluminum. And the idea that they did that is the people that sell these pans, what they do is they put a thin coating of aluminum oxide, oxidized aluminum on the inside of the pan, so that when I put my spaghetti, inside my pan, my spaghetti is not contacting aluminum metal. My spaghetti is in contact with aluminum oxide, which is even more chemically resistant than aluminum metal. So this is what I'm trying to get across is this idea of anode oxidation. That's forever, for the rest of your life. All right, any questions on that idea? All right, let's go back. What's your answer? How come the electrons don't just go here?
The salt bridge.
Yeah. So I want you to pause for a minute and think about this logically, right? If I buy a battery at Walmart, and a battery contains a chemical reaction, a redox reaction. If I buy a battery at Walmart, and if the contents of the battery on the shelf at Walmart, if those things were allowed to touch each other, the chemical reaction would go off inside the battery before I even bought the battery. And if that happened, what would happen when I took that battery home? If the reaction goes off in Walmart, what happens when I get it home?
It's done and it won't react anymore.
Yeah, I'll be complaining to the manager, say you guys just sold me a faulty battery. That's exactly what I would complain about, right? Does that idea make sense? The genius of the engineering of a battery is really clever. They put chemicals inside a battery that desperately want to react with each other, but you put this guy in the middle that keeps it from happening. And if that salt bridge wasn't there, we'll talk about a salt bridge here in a minute, but if that salt bridge wasn't there, this would touch that and they just go off and you'd be done. Okay, I'm going to ask you a pop quiz. Okay, because remember I said I'm going to give you a quiz. This is a pop quiz. Let me go back. Yeah, I'm going to use this example. Okay, remember this example? I'm going to rewrite it here. Let's say that I was going to use this chemical reaction right here, one of the ones we talked about already. Let's say I'm going to use this to make a battery. So you're saying, well, how should I know if that works for a battery? Well, the first question to ask you is it a redox reaction? Because to be a battery chemistry, it's got to be redox. Is this redox?
Yes.
How do you know it's redox? To be redox, what has to be true?
Has ions.
More than that, more than that.
Gaining and losing electrons?
And do you see somebody gaining and do you also see somebody losing?
Mm-hmm.
Okay, so good, it's redox. Okay. Next question. If it's a battery, is a battery supposed to be a source of energy, or is a battery supposed to be something you have to put energy into? Why do people buy batteries? I heard somebody say, what was it? You want a battery to be a source of energy. And to be a source of energy like water behind a dam, is lithium a metal that likes to be oxidized?
Mm-hmm.
Yep. So the fact that lithium wants to become that is like the water behind a dam. This wants to happen. All right, so now I'm going to draw my battery. Get ready, everybody. My battery. I'm going to try to keep you honest. I'm going to draw my battery differently every time so you don't get used to left and right. Okay, there's my battery. I'm going to hook a wire. Here's a wire. Okay. So let's say you're alone on a test or a quiz. Which way are you saying electrons are flowing in that wire? Clockwise or counterclockwise? Clockwise. So you're telling me that you think electrons will go this way and they'll come this way in my battery.
Yes.
Okay. Let me ask you a question then. What's happening on this side of the battery? Oxidation or reduction? Electron loss or electron gain?
Yeah.
Lost.
Electrons being produced over here, or are they being consumed over here?
Consume. Right?
It's oxidation, I think. It's losing.
Looks like it's losing electrons. Aren't they going away?
Yes.
And aren't they coming down here to the other side?
Yes.
So I'm going to ask you, this side of the battery, the negative side of a battery, is that reduction or oxidation?
Oxidation.
Oxidation. That's electron loss. If I come down to the other side of the battery, is that reduction or oxidation?
Reduction.
It's got to be reduction. It's got to be electron gain. Now, y'all stop me if you don't like what I'm saying. So now I'm going to ask you a question. If I was to cut this battery open, didn't you say we should cut batteries open?
Yes.
Okay, well, you're gonna have to do that on your own with a hacksaw. Okay, be careful. Okay, be careful. It's definitely worth your time to do it. Do it someplace where the stuff doesn't get all over everything. Wear some gloves. Anyway, here's my question. If this was in my battery, which side of my battery is the silver ions? Are the silver ions on the positive side of the battery, or the silver ions on the negative side of the battery?
Negative.
All right, so you're telling me, try it. I mean, is the silver ions where the electrons are going? Is the silver ion gaining electrons, or the silver ion losing electrons?
Losing.
Remember our half reactions that you and I wrote down some time back? We wrote a half reaction for silver that looks like this, right?
Oh, no, it's gain.
So is this electron gain or electron loss?
Gain.
So is the silver going to be down here or up there?
Down.
Silver ions, if you cut your battery open, and if this was the chemistry that was in the middle of your battery, you literally would find silver ions on the positive side of that battery, because that's where electrons are going. And I don't know if you know this, but people who make math, I'm not encouraging you to make math, right? So don't put this on you. That's not what I'm doing, but it's a good example. People used to use lithium batteries, and probably still do use the lithium in lithium batteries in order to make meth. And so they would cut the battery open, and they had to know on which side of the battery the lithium metal would be found. So Where's the lithium metal in this battery? This guy right here. Remember, lithium metal is going to undergo this half reaction. Where's the lithium metal?
On the negative.
Negative.
Yeah, so you're saying lithium metal. So let me see if I understand this. You're telling me that lithium metal will do this chemistry and will lose electrons. Where do those electrons go? Well, they go out this side of the battery, they come down the wire, they pass through my cell phone or my laptop computer, and they come to the other side. And what do they do when they get to the other side? They encounter the silver ions, gain electrons, and become silver metal over time. Okay, this is overload. What do y'all think? Is that okay? Let me stop and you ask the question. Everybody okay with what we're saying? Ask me questions if you have them. If you don't want to ask me right now, that's fine. You can shoot me an email and I'll do that. But if you have a question, go ahead and ask.
I'm still confused on how do we know this equation was redox or not.
Oh, good question. Who can answer Mike's question? Mike wasn't. Let me go back and erase my check mark, Mike. So we didn't check that off.
Didn't you say
how do you know it's
if
redox? How do you know?
Didn't you say if it gains or if it loses an electron?
So let me ask the whole class. I heard that. I like what was just said. Who was that?
Me. I'm just playing this Trinity.
Yeah, you can't say me. Okay, so yeah, Mike and the whole class. You need to know that redox is when you have a combination of somebody losing electrons and somebody gaining electrons. And right here, I got silver ions losing electrons, and I got lithium atoms gaining. I'm sorry, back up. Silver ions gaining electrons to become silver atoms with no charge. And I got lithium atoms losing electrons because they have no charge, losing electrons to become positively charged. Mike, you're going to have to look at the charges to see if you can tell if somebody is losing electrons and somebody's gaining electrons. And if you find that happening, Mike, that's screaming redox.
Okay.
That's how we know. So it's actually really important that everybody in the room knows about our charges and the difference between a positive ion and a negative ion and atoms that have no charge. All right. Any other good questions, Mike? Thanks for asking. That was a good question.
No problem.
Miriam, I see your name flashing across there. Welcome. We got marketing stuff. We had marketing. All right. Okay, so I'm gonna go. Let's go back to where we're at before. Okay. Talked about that. Talked about this. This. Okay. We're gonna spend a little bit of time talking about salt bridge. Okay. Spend a little time talking about a salt bridge. In order to do that, let's see. I'm gonna go to the internet. To read my emails. Okay, there's our outline. Did y'all see the quiz on April 2nd? On the wrong days, whatever the Thursday is after spring break. Okay, so let me go here. All right, why think Powerade? Right? Did you ever wonder?
Isn't it because of electrolytes?
Yeah.
What does that mean?
It replaces the stuff you lose in sweat. That's all I know.
Well, let's look and see. Yeah, okay. Look at these people. I mean, I'm not just saying because LeBron James says I should drink it, or some other famous athlete. Let me see what it says. Powerade contains 4 electrolytes: sodium, potassium, calcium, and magnesium lost in sweat. These guys help you retain fluid, so you stay hydrated, and muscle flow and blood volume. Without these electrolytes, your urinary output increases, and you're going to get dehydrated, and that's not good. And we won't get into which one's better for you, Powerade or Gatorade, because Miriam, then we have a marketing problem in front of us. Okay, let's not do that right now. Okay. All right. So what the heck is that? What is that? So that's the idea. Let me go back to my picture. That's the idea of our salt bridge. Okay. A salt bridge. Whenever you hear the word salt bridge, this is saying like Powerade. This is saying that the salt bridge contains an electrolyte. In fact, I would bet my life on it, okay? I would bet my life that it has a electrolyte in it. Here comes the confusing part. Get ready. Let's look over here on this side. What's the formula of this compound? This is a compound that contains sodium ions and chloride ions. What's the formula of sodium chloride? How many sodiums and how many chlorides does it take to make a compound?
And
2 sodiums and 3 chlorides, or 1 of each, or 2 chlorides and 1 sodium, or how many each do you need?
1 of each.
1.
Okay, and why is it just 1 each?
It charges 1.
I only take 1 positive to counteract 1 negative, and if I do that and I put them together, I'm going to get a compound, and this guy would be a beautiful snow white solid, and we'd call it sodium chloride. And oh my goodness, do I love salt. Okay, I love potato chips, I love peanuts. Sorry, I'm getting talking about food right now, but okay, I love to eat salt. Salt and greens are my 2 favorite foods, okay? So if I eat salt on potato chips, it is this compound right here. This is sort of like a close-up. And you can see that the sodium ions are packed in there with the chloride ions. This is like a crystal of sodium chloride. Now, I know you have all put salt in water. Here comes the interesting part about water. This is a water molecule right here. It turns out, for reasons we'll talk about in the next chapter, water has a negative side and a positive side. Okay, as it turns out, it's a polar molecule. The way that batteries have a north and south pole and or plus and minus pole, water's got both a negative end and a positive end. And it turns out that when these guys get put in solution, you see how the negative end is pointing towards the positives? And see how the positive end is pointing toward the negative? The water's literally, imagine that you put, let's say I got a pack of wolves, and I threw a box of steaks in a pack of wolves. The wolves would be ripping the box of steaks apart to rip the steaks apart. I mean, you know what I'm talking about. Water is like a bunch of wolves. Because water has a positive end, because water has a negative end, it walks up to these guys and just pulls it apart, and pulls it apart, and pulls it apart, and pulls it apart. And so the idea is ionic compounds, like water, can be broken apart. Water is not an ionic compound, sorry. Ionic compounds like salt can be broken apart and broken down into their separated mobile ions. And so anything that makes mobile ions, meaning ions that can move around, would be an electrolyte. Then Miriam, you'd have to help us with this. Why doesn't Powerade say the word mobile ions? And you'd have to answer that question. I think that would be unfair. I mean, who would buy Powerade if we talk about mobile ions? Electrolyte is scientific enough. We don't need to talk about ions, okay? So they don't need to mention it. But you're sitting in a chemistry class, so you need to know that whenever you see the word electrolyte, that means that there are ions that are mobile and able to move, okay? And that's what it provides. All right, so the question is, why does that matter in a salt bridge? And get ready, you and I are going to draw another battery, right? Give me a blank piece of paper. And I'm going to delete that. Let me draw another battery. I need to draw the battery a different way this time. Okay, I'll draw the battery like this. Let's say I put the positive end down here. And I got the negative end up here. And here's my wire. Okay. Which way are electrons flowing through that wire? Clockwise or counterclockwise?
Counter.
So we got electrons, right? Electrons are flowing counterclockwise, which would be this direction, or they flow in this direction?
Clockwise.
Clockwise. Electrons are going to go this direction and this direction, right?
Yeah.
Where's the salt bridge in this picture?
In the middle.
Right here. Right there's my salt bridge. Let me ask everybody, what if I sold a battery without a salt bridge?
Get your money back.
Why? Why? What's wrong with leaving out the salt bridge?
Because I mean the battery already reacted. think
Think
that's
about
right.
it. If that salt bridge, yeah, I heard Mike saying it. If that salt bridge wasn't there, wouldn't these two chemicals touch each other?
Mhm.
Then the chemistry would go off in the middle of the battery, and the electrons would never have a reason to leave the battery. And Mike, it would be a failure right from the beginning. You're right. All right, so get ready. Everybody ready? We said mobile ions, didn't we? That's what's in the middle of my salt bridge, because that's my electrolyte. That means my mobile ions contain positive ions, and it contains negative ions. So now I'm going to ask you a question. Right here in my salt bridge, which ions are moving in this direction? Positive ions or negative ions?
Positive.
Positive.
And before you answer that question, I heard some answers. I'm going to draw a circle. And physics has decided that if all the negative things are going in this direction in my circle, then which direction are positive things moving?
The other way.
They're moving in exactly the opposite direction. And before you answer that question, or before you ask a question, think if that makes sense. We got a loop, and in a closed loop, I got negative things moving in one direction, and I got positive things moving in the opposite direction. Are y'all okay with that?
Whoa.
Mike, you okay with that?
Yes.
All right, so now come on back to my battery. I want you to think carefully. Okay, I'm going to draw it like this. Let's imagine that the battery's not there and that this is a loop. Electrons are negative, right? My negative ions are also negative. Do they have to be moving in my salt bridge the same direction as the electrons or the opposite direction of the electrons?
The same.
They have to, don't they? I got my negative ions going in that direction. And I know why you're uncomfortable with that. You say that doesn't make any sense. Why would negative guys go to the negative side of the battery? And let me argue it to you two ways. All my negative guys got to be moving in the same direction, just like this picture over here. And all my positive guys got to be moving in the same direction, because this is a loop. And if you think about it, every time an electron leaves, that has to be made up for. In other words, in order to keep this end of the battery happy, when an electron leaves and go to the other side, a negative ion has to move in and replace it. Otherwise, you'd end up with charge getting built up on one side of the battery. How we doing?
Wouldn't salt ions be positive though?
Salt, if I go back to my picture, take a look. Good question. What a good question. All right. Doesn't any ionic compound contain both negative and positive?
Mhm.
So let me go back to my picture. So this would be like the chloride ions, and this would be like the sodium ions. And so chloride ions in my salt bridge, if that's what was in my salt bridge, and we're moving in this direction. So then which ions in my battery are moving in this direction? Inside the battery, I didn't say through the wire. Electrons are what moves through the wire. Which ions are moving in that direction?
The positive.
My sodium ions, or whatever my positive ions are. How we doing? All right. So I'm gonna try one. See if you. I'm gonna give you all a pop quiz right now. So you're gonna need a blank piece of paper. I'm gonna write it up here. Okay. All right. I'm gonna give you a chemical reaction. These chemical reactions can be I don't know, copper and silver. And it's gonna make like that. Okay. So if this is on a quiz, first thing I would ask you to do is I would ask you to balance this reaction if this was a quiz? Then next question I would ask you is, could we use this for a battery? I might ask you that. Next question I might ask you is, which one of these metals, silver or copper, would be at the anode of this battery? Which one of these metals would be at the cathode of this battery? Let's start with that. Okay. Take some time. I'm gonna watch the clock. Right now my clock says 11:51 Arkansas time. I'm gonna give you 3 minutes to come up with some of that stuff. See if I can be quiet for 3 minutes. It's the longest 3 minutes of my life. I'll bite my tongue. See, Mike knows I can't be quiet. See, he knows. Two more minutes. One more minute. No pressure. We only got about 12 minutes of class left. All right, my clock says 11:54. So let's see. Let's say I got this on a quiz. I probably should have asked this question first, maybe. Hey, everybody. Could this be used for a battery? That's a yes or no, black or white question. Could you use this reaction for a battery?
Yes.
Okay, I heard a yes. Is that a yes with confidence? How do you know yes or no this could be used for a battery?
In a redox.
How do you know it's redox?
Because it's gaining and losing electrons.
Well, who's doing what?
Copper is
Gaining electrons over here.
Copper is
So something's happening to copper. Copper's going from here to here. Is it electron gain or electron loss?
loss.
All right, let me look at this. An electron loss. An electron loss, last time I checked, means what?
Oxidation.
Oxidation. Okay. Well, then somebody has to be reduced. Who's reduced?
Silver.
So this guy is going from here to here. That's electron gain or electron loss?
Electron gain.
Electron gain. And that's reduction or oxidation?
Reduction.
Reduction. So which one of these is the answer? Could it be used for a battery?
Yes.
The answer is absolutely yes. If you're not sure of that, you should ask me right now. Because this is the way I would do it. Who's gaining and who's losing? Yeah. Now, here's my advice on the balancing the reaction. I would take this guy. There's different ways to do it. One of the ways you could do it is to break it down into the two half reactions, right? We got reduction and we got oxidation, right? Let's do it in pieces. Silver is electron gain. This is becoming this. To balance this, which side would I have to put electrons? On the product of the reactant side.
React.
I need electrons over here or electrons over here.
Reactant.
If I put an electron here, this negative and that positive makes no charge right there. Let me try the other one. Copper turning into this. Which side do I need electrons here?
Product.
You sure on this side? Why not over here? This is no charge. But if I put two negative guys over here, that makes no charge, and that equals that right here. All right, let me stop. Everybody okay with that? If I was going to add these together, add them together, and come up with an overall balanced reaction, I think Matt or somebody or Dylan said this earlier. Well, what do we have to think about when we're adding two half reactions?
Common multiple.
I heard something. What was it again?
The least common multiple or
Common
something.
multiple. Okay. Who's a common multiple of 1 and 2?
2.
Okay, so how do I get? I got 2 here now. How do I get 2 up?
Just multiply everything by 2.
Everything by 2. That's going to make 2 electrons, which will cancel those. That'll make 2 silvers, ions, and 2 silver atoms. And so when I come down and I bring all this stuff down, that's those guys. I got 1 of those plus 1 of those, 1 of those, and 2 of those. How we doing? All right. Now I want right here, I want you to draw a battery. I want you to label anode and label the cathode. I want you to tell me which metal's on which side of the battery. I'm gonna make my battery look like this. Say it's positive on this end and negative on that end. Take a second and label the anode and the cathode. Which metal's on which side of the battery? Is the silver on the positive side or is the silver on the negative side? Is the copper on the positive side or is the copper on the negative side? Get me a wire. Make a orange wire. I'm alone on a test. I always draw a wire. Which way are electrons flowing through my wire? Clockwise or counterclockwise?
Counterclockwise.
So electrons are going counterclockwise in this direction, right? They're leaving here and they're coming around and they're going here, right?
All right.
Good.
This over here, is that electron loss or electron gain?
Okay.
Loss.
Which is it? Loss or gain?
I think it's loss.
Loss. Okay. Which of these two then is happening on the right?
Copper.
Copper's over here, right? Because the copper is becoming copper ions, and these 2 electrons are the electrons that end up going through the wire. On this side, I got the silver ions, right? And that's where the electrons are going to. Anode to cathode. Which one of these is the anode? Which one of these is the cathode? Remember, what does anode mean?
Anode is oxidation.
Anode's oxidation. Which side's oxidation, copper or silver?
Copper.
This side over here is oxidation. You got the anode or the cathode?
Anode.
And oxidation, yeah. And then this one over here is reduction. That's got to be the cathode. And I'm telling you, when I do these kind of questions, I always draw the picture. Okay, because it's very black and white. There's no gray. It's either oxidation or it's reduction. And so draw a picture, and you'll less likely to get it wrong. I got one last question, and we're going to end on this last question. Okay. Let's say, pick a different color. I'll make it pink. Okay. Let's say I have to. I got a salt bridge in the middle, don't I? And let's say that salt bridge contains sodium ions and iodide ions. Which ions in my salt bridge are moving in this direction?
Sodium.
I heard to vote for sodium. Somebody said sodium. Why are the sodiums moving that way?
It's positive.
They're positive and they move in exactly the opposite direction of the negative guys. Y'all see that? And which ions in the salt bridge are moving in this direction?
Iodide.
So I minus is moving to the right and sodiums are moving to the left. What would happen if we didn't have a salt bridge?
The battery would be reactive.
It would go off on the shelf. And it would take about 2 seconds to be all done, and then they'd have a pile of nothing. They could sell to nobody. So you got to have the salt bridge to keep them from touching. All right. I want to end, and I just want to remind you of a couple of things. Okay? Let's see. Did we talk about that today?
Yes.
Did we talk about that today? Talked about that, right? And we talked about that. What kind of metals are good for making jewelry? Ones that are easy to oxidize or hard to oxidize make good jewelry.
Hard.
Right. So then what do you have to put in a battery? Do you have to put metals that are easy to oxidize or hard to oxidize in a battery?
Easy.
Yeah, you're definitely going to have. That's why lithium is so popular, because it's a metal that's easily oxidized. We didn't talk about this, but we'll pick up on that next time. I will be here at 3 o'clock today, right here. Okay, very same place if you got questions. That's today. Does everybody know that they're talking about lifting your registration on the 24th? Have you heard that? You normally have to see your advisor, right? My understanding is that since we're all away from each other, they're just going to go ahead and do that. Okay. So what I really need, I think what the whole campus needs is on March 24th, not like first thing in the morning, but sometime March 24th in the afternoon, please check to make sure your registration hold has been lifted. All right. If it hasn't, you can contact your advisor ASAP. Okay. And or me. I mean, I'll be here. You could shoot me a email at my email, and I'll see if I can't help you. But make sure that's good, because some of you, I think, some student athletes and students at honors college, you can register, I think, on the 25th. I think, right? And if you're bored, and I know you're not, but if you're bored, you ought to go read about the amazing women in chemistry. Okay, these are it's about 20 different very successful female chemists who are changing the world around us, even as we speak. And like I said, sometime over spring break, I'm going to put these videos together, so I'll be getting that ready. And Thursday when we come back is when I want to plan to have a quiz. And as I told you on the syllabus, the quizzes will be they're going to be something you're going to do away from class. Okay, I'll have it set up that way. And I'll have very clear. I think what I'll do is I'll turn the link on, and I'll turn the link off in a 6-hour window. And everybody's going to hand their stuff in using that. Somewhere I got a place to hand in assignments. Right here. You go right here. So when you go to hand in stuff, you're going to tell me what your name is. You're going to tell me what you're handing in. and then you're going to upload your file. So if this is a problem, let me know.
Is the link being uploaded like at the beginning of class times?
No, I think what I'll do is I'll sort of time it artificially. Like I will post the link at a certain time to be made clear on the website, so you'll know whether it be noon or whatever time. And then I will turn off the link, which means you can no longer get it. Okay. And so I'm gonna have I'm gonna limit the so in other words, if it's more than 6 hours, well, I don't have to do it here because this will tell me when you hand stuff in. I'll know when you hand it in. Okay, so don't wait forever. But if I go back to that, I'll post the link at a certain time, and then I'll count 6 hours, and anything after that time when I posted it would be marked late. Okay, so don't be late. Go
I'm
ahead.
just worried about like knowing when it's posted so that we know what our time.
Oh, good question. Good question.
So that's why I was
Well,
asking, like, do we have a set time, like a beginning or end of class?
I think what I'll do is I'll probably post it after class is done.
Thank you.
That help? Let me make a note. I'll do that right now. Why don't we say 1 p.m. Quiz is active. How about that?
Yeah.
And so you'll have from 1 p.m. until 7 p.m. to get the thing done. And it'll still take you 10 minutes. It won't take you forever. But that will allow for bad internet and all the rest of that. Please, 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 if you give me handwritten stuff, make darn sure that whatever you give me scanned is clear, okay? Because I don't want to read dark things or I can't read the writing. Make sure it's clear. You can type it if you want to. All right, any other questions?
And you said the question sheet will be posted
Which question?
at the same time that the link is live?
Yeah. So when I say the quiz is active, that means the quiz will be right here, and you'll click on it, and you can download it and do it.
All right, thank you.
All right, any other questions?
When are we supposed to get that email about our graded work and stuff?
I'm actually doing that right now. I spent some time yesterday grading, and so believe it or not, I'm actually collecting the stuff because what I'm going to do is there's probably different ways we could do this. You could probably share a Google. If you shared a Google folder with me, I could put your graded work. I just don't want everybody to see each other's graded work, you know. So what I'm going to do later today, I'll tell you what. Later today, I will have stuff given back to you by email, and so you should expect to see it in your email. How late today? I'm not sure. It could be 6 o'clock, but it'll be later today. So as soon as I hang up, I'm going to work on that right now. Any other questions? All right, y'all. Don't look for this recording to be available right away. It's going to take a while, I think, for it to be rendered. But I'm going to try to look back here in about 30 minutes, and maybe it'll be on the website. All right, y'all. Take care.
Thank you.